and he will be speaking on inverse semigroups and Cuntz-Li, or rather the other way, Cuntz-Li algebras, Cuntz-Li relations and inverse semigroups.
Okay. So, thank you. Let me first thank Vijay for asking me to give a talk here. It's a great honor to give a talk here. And before I get into my talk, let me thank Sundar for the following reasons. So, thank you for being a great teacher to me, and thank you for introducing me to operator algebras, K-theory, and eventually to my advisor Partho. And finally, thank you for putting up with all my tantrums. Thank you very much. Wish you all and happy birthday. Thank you. So my title of the talk is Cuntz-Li relations and inverse semigroups, but this is the same talk that I gave at ISI Delhi some time back, so I forgot to change the title. And it's so this is something which Cuntz and Li and their collaborators are doing at Munster currently. So they want to attach C-star algebras to rings and ask properties regarding that. So the setup is the following. So start with an integral domain which has only finite quotients. So finite quotients means every principal ideal AR has finite index. So it has only finite non-zero quotients. So what are the examples of such rings? Integers, because every ideal in integers is of the form mz, and the index will be m. And you take a number field K, which is a finite extension of Q, and then look at the ring of integers in a number field. That is another example of an integral domain which has only finite quotients. Okay. We all know how to attach a C-star algebra to a group. A ring has two operations. One is addition and multiplication. So Cuntz considered this C-star algebra. So look at the L2 space. Look at the L2 space L2R and look at the unitaries on L2R induced by additions. So delta R is the standard orthonormal basis, and look at the unitaries induced by the additions. And look at the isometries induced by multiplications. So multiplication is not surjective, so that's why it's not going to be a unitary, it's only going to be an isometry. It will be an isometry because you are considering an integral domain. So R going to AR is an injective map, so it's going to be an isometry, and it will be a bounded operator only if A is non-zero. If A is 0, then you are sending everything to delta 0, and so it's not a, so we consider only these two families of operators. One is coming from the addition operation of the ring, and another is coming from the multiplicative operations of the ring. So Cuntz in his first paper considered this for R equals Z, and also for the monoid R equals N, the natural numbers. And then Li and they studied in more general situations, and Li even has studied it for non-commutative rings and so on. But I am familiar only with this setup. So anyway, so for every element in the R, look at the unitary induced by the addition, and look at the isometries induced by the multiplication, and look at the C-star algebra generated by them. So that is the ring C-star algebra associated to R. So what are the relations that they satisfy? So
sorry, 1 minute. This previous slide, so in the last slide, something about the final space of S A.
Yeah.
The previous.
Yeah. So the multiplicative operation will give you an isometry, but the final space, what is the range of SA? The range of SA will correspond to the ideal AR, right? Because delta AR, and so it will correspond to the ideal AR. So these satisfies these relations. Obviously, that if you add by n and add by m, it's same as adding it by m plus n. And the same thing, SA SB is SAB, and this is the distributivity relation. This is the relation between the The third relation is the relation between the multiplication and addition. If you first add by m and multiply by a is same as multiplying by a and adding it by am. This is the distributivity law. So the first three conditions are basically restating the ring relations. This is the additivity of the addition and this is the multiplicative of the multiplication, and this is how they interact. The last relation is the finite index condition, that is EA will correspond to the ideal AR. So if you translate it by this UM, that will correspond to the coset M plus AR. So R by AR has finite index, so if you add them it will be 1. So these are the Cuntz-Li relations for a ring, and so we can make a definition. So consider the universal C star algebra, that is called the ring C star algebra associated to a ring, generated by a set of isometries SA for A non-zero and a set of unitaries UM with M for every R satisfying the above relations. So the last condition is the finite index condition. The remaining conditions are just the ring relations. Okay.
The existence of universal C-star is obvious.
Yeah, you just take polynomials in UM and SA, and if you demand them to be unitary, this UM will have norm less than or equals 1 and SAs also will have norm less than or equals 1. So you look at the star algebra generated by UM and SA and put this soup norm, and moreover this is a concrete representation of the universal C star algebra is the reduced C star algebra. The reduced C star algebra is the one which is on L to R induced by the addition and multiplication operations. So there is a natural map from UR to U reduced R with sending small SA to capital SA and small UM to capital UM. Okay. So what did Cuntz and Li proved? Cuntz straight away proved that this algebra is simple and purely infinite. So simple means it does not have any ideals, and purely infinite means every hereditary C star subalgebra contains an infinite projection. An infinite projection is one which is equivalent to a proper subprojection, and he proved that this is simple as well as purely infinite. So because it is simple, the natural representation from UR to U, the regular representation is actually an isomorphism. Because it's simple, it does not have any ideals, so it's going to be 1 1. And he also proved that this is actually Morita equivalent to a cross product. The form of this C star algebra is actually obtained by cutting down a cross product by a projection. I will explain this with an example. And in fact it is actually a groupoid C star algebra. So this Morita equivalence is of C star algebras is exactly like that of rings. You say two C star algebras are Morita equivalent if there is two C star algebras A and B are Morita equivalent if there is a AB bimodule and another BA bimodule, such that if you tensor them you get your original A and B. So the Morita equivalence will so Morita equivalent C star algebras will have same representation theories and so on. Okay. So let me illustrate with this with an example what is this cross product and what is this groupoid. So what is the form of this universal C star algebra UR? So this is again Cuntz result. So consider the ring, the familiar ring integers, ring R equals Z. Then look at this space. So AF is this product QP, where QP is the periodic completion of Q. Look at the Cartesian product, but you demand that only finitely many of them are outside ZP. And look at so this is called the ring of finite adults in number theory, and look at this Cartesian product ZP in AF. This is going to be a subgroup of AF, and this is actually a locally compact group. You can give the Cartesian topology on this and give the subspace topology, and this is going to be a compact open subgroup there. Okay, I need this. So this is called the ring of finite adults, and this is the compact open subgroup sitting inside there. So moreover, this so QP is the completion of Q with the periodic metric. So Q will be sitting inside QP for every P, and so you can let Q, there is an embedding of Q in AF. You just embed it x going to xxx and so on. But you can prove that for only for finitely, except for finitely many primes, any rational will be in ZP for the thing. So there is an so AF is a ring actually, and it will contain Q. Q is the rational numbers. Okay. Okay. So look at this cross product. So Q is a ring which is sitting inside AF. So Q will act on AF by addition, and Q star, or this is the set of non-zero elements in Q, and that will act on AF by multiplication. Actually, the ring of finite adults is actually a ring and which contains Q as a subring. Therefore, this semidirect product. So what is this semidirect product? You look at Q as an additive group. You look at the multiplicative group Q star that acts on Q by multiplication. So looking at the semidirect product is the same as looking at the field. So look at this semidirect product. This will act on AF, where Q acts on AF by addition and Q star acts on AF by multiplication. And you can form this cross product. And Z hat is a compact open subset of AF. So indicator of Z hat makes sense as an element of C0 AF, and I cut it down by that projection. And it's Cuntz-Li proved that such a C-star algebra is isomorphic to this. From here, the second line is not very difficult to prove. The second line is that you just have to argue that, so this equivalence with M is that Morita equivalence. It is not difficult to prove that this is Morita equivalent to this. The only thing that one needs to argue is that this projection P, this projection 1 Z hat, is actually a full projection. That is not difficult to show. But the remarkable thing about this thing is, this is also Morita equivalent to this cross product. This is familiar to us. So look at Q acting on R by addition, Q star acting on real numbers by multiplication, and that will induce an action of the semidirect product on C0 R, and so you can form this semidirect product. It's also true that this is Morita equivalent to this, and this Morita equivalence is now called Cuntz-Li's duality theorem, and this Morita equivalence allows them to compute the K groups of such kind of C-star algebras. So this is the thing for R equals Z. So for R equals number field also a similar result holds. So here it is the ring of finite adults. The ring of finite adults makes sense for any number field, and what is R here is, R is the completion of Q with respect to the usual Euclidean metric, right? So this is called, I mean, you look at the completions at infinite places. So there is such a construction for any number field. So this is enough for us. Okay. Okay. So the first line says that the ring C-star algebra is isomorphic to this cross product cut down by a projection. So in the groupoid language, this is same as saying you look at, so this group acts on this set, and so you can form the groupoid associated to that action, that is the transformation groupoid, and Z hat is a compact open subset of AF, and you restrict that to Z hat. So the first one is equivalent to saying, I'm not going to define what's a groupoid and what is a C-star algebra associated to a groupoid, but the first line is equivalent to saying that this is isomorphic to the C-star algebra of this groupoid restricted to this subspace. Okay. Okay, so how to arrive at this groupoid realization? So how Cuntz and Li arrived at this thing is, they straight away proved that this C-star algebra is simple, and they gave a homomorphism from UZ to this corner of this cross product. So they straight away proved that this is simple, and then they proved it is isomorphic to this corner. But there is a very conceptual way where one can arrive at this isomorphism, that is if you use the language of inverse semigroups. So if you use inverse semigroups, then this will be a sort of, you arrive at it naturally rather than you don't have to guess anything. So you don't have to guess what are the ideals here and so on. That will be a consequence. So okay. Before I show how inverse semigroups will give you such a thing, let us do a bit of generalization. So this generalization is initially due to, let me put the next slide also, no. So this generalization is first due to Quick, Landstad and Kaliszewski. So you look at a semidirect product, n semidirect product H. So in the ring case, for example, when R is Z, the semidirect product is Q semidirect product Q star, and I am looking at a subgroup of n, a normal subgroup of n, that normal subgroup there is Z. So in the case of the ring, in the case of an integral domain, you look at the semidirect product Q semidirect product Q star. In the general case, you look at K semidirect product K star, where K is the field of fractions, and M is the M is R itself in that case. And you look at so H acts on n by conjugation, and you look at the elements of H which leave M invariant under conjugation. So this will obviously form a semigroup or a monoid. It will contain identity, one will be there, and it's a semigroup. So we assume the following conditions, that is H equals PP inverse equals P inverse P. So this condition is called the OR condition. I'll explain that, what does it mean. And we assume that these conjugates of M are a finite index in M, and this intersection A inverse is identity. Okay, so we don't have to assume H is abelian, but rather it's enough to assume this is called OR condition or OR reversibility condition. So what does that mean is, so you have a semigroup P and assume it's cancellative. So cancellative means it has cancellation, it obeys cancellation law. Then you can construct a group of fractions for it. So basically you can construct a group G. When you can construct a group of fractions for it, that's called OR semigroup. A semigroup P is said to be right reversible if PA intersection PB is non-empty for every A and B in P. So if you have this condition, then you can form a group of fractions for it. You can form a group H which is such that P is a subgroup of H and every element of H can be represented as a fraction of P. Okay. So what does this mean to say? So basically the proof of constructing the H is basically imitating the Grothendieck construction. So how you construct integers from natural numbers. You can do the same construction given this situation. So what it means to say PA intersection PB is non-empty, this means there exists alpha and beta such that alpha A equals beta B. Yeah, I wrote this because Sundar would insist on using a better notation. So he will insist on writing this as beta A equals alpha B. Beta A equals alpha B. The reason is, if P is abelian, the choice of alpha is A and the choice of beta is B. So it's so anyway, that's why I wanted to write this. That is not the reason. So basically this condition, the condition that so I have written H equals PP inverse. So the fact that PP inverse is actually a group is actually closed under, it's closed under inverse, but the fact that it is actually forms a subgroup, if you think about it, you will end up with this condition, that is the PA intersection PB is non-empty for every A and B. Okay. So given this, you need basically this condition will allow you to construct a group of fractions. It will allow you to do the Grothendieck construction for this semigroup also. Okay, so you have the semi-direct product, you have a normal subgroup M. Now what is the Cuntz-Li algebra generated with respect to this is, for every element A in P, you consider an isometry SA, and you look at unitaries UM for which these relations are satisfied. So this is the group relation in H, and this is the group relation in N, and this is how they interact, the two groups interact. And the final condition is that if you take the union of all cosets of the conjugates, you end up getting 1. Okay. So the same case was considered when H is abelian by these 3 people, but one can do better. You don't have to assume the commutativity of this group. It's enough to assume this OR condition of the semigroup, the reversibility condition on the semigroup. Okay. So what are the examples of such a thing? So you look at the Cuntz-Li setup. So there you had an integral domain R. So look at its field of fractions K and form the semi-direct product K star and take R as the normal subgroup of K. So if you take that, then the Cuntz-Li algebra associated to a ring is actually a special case. So another special case, another example is, you look at an n cross n matrix, all whose entries are integers. It's an integer dilation matrix. What is an integer dilation matrix? Is all the entries of A are integers and all its eigenvalues are of absolute value greater than 1. So it's invertible, and determinant of A is modulus of determinant of A is greater than 1, and all its eigenvalues are greater than 1. Now let that matrix act on q power n by matrix multiplication and form the semi-direct product, and take your normal subgroup Zn to be normal subgroup to be Zn. You can check. Yeah. It is invertible over Q but not over Z. So yeah, so I need such a kind of thing. So you can check that for this thing also the previous conditions are satisfied. And the more interesting thing is, you look at a subgroup of GL and Q, it is just you are looking at a single matrix. You can also have a subgroup of GL and Q acting on Q power n, and you take a normal subgroup Zn of Qn. So you can take gamma to be GL and Q, for instance. So this is the higher dimensional analog of Cuntz-Li. If you take n equals 1, and if you take gamma to be GL1Q, you are taking the semi-direct product Q semi-direct product Q star. So okay. So what you can prove is, you can prove that this C star algebra can be realized as a groupoid C star algebra, and using this one can consider one can answer things like simplicity and so on. And more importantly, you have this nice duality theorem. You have this nice Morita equivalence. That is, you look at so look at a subgroup of GL and Q acting on Q power n, and look at the Cuntz-Li algebra associated to such a thing. Then that is actually Morita equivalent to this C0 Rn. So Qn acts on Rn by addition, and gamma is a subgroup of GL and Q, so it will act on Rn by multiplication also, but you have to take gamma opposite. So the gamma opposite is I mean gamma opposite is gamma only, but that will act on Rn by gamma transpose instead. So, so these are the things obtained. So the main so the inverse semigroups come when you try to realize this C star algebra as a groupoid C star algebra. So how to realize that as a groupoid C star algebra? Okay. So what are inverse semigroups? An inverse semigroup is an inverse semigroup if for every element S there is a partial inverse. It does not have inverse, but it has a partial inverse. So S star S, S star is S star, and S S star S is S. This is just the relation for a partial isometry, and it is for this reason it's interesting. It plays a role in operator algebra. So what is an example of an inverse semigroup? You consider a set X and look at all partial bijections on it. So what do we mean by a partial bijection? An element in Ix consists of three things: a domain, a codomain, and a bijection from a domain to codomain. Even an empty function is also a partial bijection. So that is like the 0. So if you don't like partially defined maps, you take a partial bijection, look at the operator on L2x. So you take delta x, and if it is there in the domain, apply phi. If it is not in the domain, you apply 0. So clearly this is a partial isometry, and this is going to be a semigroup morphism. And it's also a theorem due to Wagner and Preston that any inverse semigroup embeds into such a thing. This is like the Cayley's theorem for groups. Any inverse semigroup is actually a sub-semigroup of partial bijections. Okay. So thus an inverse semigroup is nothing but a semigroup of partial isometries. What? No, it's okay. So no, this is 1963. It's Wagner-Preston is even 1960 or 50. I don't know. It's very far.
You said it's like Cayley's theorem. Is that X constructed out of S naturally?
Yeah. So yeah, X is actually constructed out of S. So you look at domain of S as actually for an inverse semigroup. If you look at the set of projections, that forms a commutative semigroup, and using that you do it. Okay. So an inverse semigroup is nothing but a star semigroup of partial isometries. So it consists of partial isometries, but composite of partial isometry is again a partial isometry. It is not true in general that if you take the product of two partial isometry, it's again a partial isometry, but an inverse semigroup is one which consists entirely of partial isometries, but which is also closed under multiplication. So a useful fact is that the set of idempotents in inverse semigroup actually forms a commutative semigroup. So using that you prove that theorem. Okay, so you can, for an inverse semigroup again you can attach a C star algebra. So you would like to find a C star algebra whose, so you want to represent your inverse semigroup elements as partial isometries on a Hilbert space. So you look at the enveloping algebra corresponding to that. So you look at you form this span of delta S or whatever, and then that will form a star algebra, and look at the enveloping C star algebra of such a thing. So it's a theorem due to several people. It was the relation with inverse semigroup and groupoids was first observed by Jean Reynaud, and after that it was proved by Alan L.T. Paterson. So it was this theorem, this C star algebra is always a groupoid C star algebra, was proved by Paterson. So what is Paterson's groupoid? So you look at the set of idempotents that forms a commutative semigroup. You look at the set of characters of that idempotents, and then give that space that pointwise convergence topology that will make it into a compact Hausdorff space, and your S will act on E hat partially, because S will act on the set of projections partially. If E is a projection, S star is again going to be a projection. So it will act like that. So the action is, I'm letting it act on the right. So you take a character X x dot S acting on E is x of SE S star. So S acts on SE S star is again an idempotent, so that will induce an action on the characters. But it's again it's sort of it's a partial map. It will act on it will act from DS to RS. So, and then Paterson's groupoid is the groupoid of germs for this partial right action. So, what is an element of G? An element of G is an equivalence class XS, where X is in the domain of S. So, X is a character and XS is identified with YT if X and Y are same, but there is an idempotent E such that ES equals ET. That is, S and T in a neighborhood are the same. So, I won't. So, this forms, and then you define your multiplication for the groupoid and the inversion this way. So, I mean, I have written it like it is, the multiplication is defined everywhere, it is not defined. It's, so the domain of the range of XS is X, the domain of XX is X dot S. So, in the groupoid multiplication is defined only if the range of this coincides with the domain of that. If the range of the first one here coincides with the domain of the second one here. So, the theorem due to Paterson is the C star algebra of S is isomorphic to the C star algebra of the groupoid G, where G is constructed out of S in a canonical way. Okay, so let us come back to our Cuntz-Li algebra. So, it contains this isometries SA and the unitaries UM. So, look at the range projections of SA, that you call it by EA. So, from EA you can construct these kind of projections. You simply translate, you simply conjugate these projections EA by your unitaries UA. That will again be a projection. The thing is that last relation, that is, sorry, so this last relation, that is, this will tell you that these idempotents actually form a commutative thing. That is, if you take they are all projections and the sum is 1. So, if you take any two of them from the same coset MA, their product is going to be 0. But if you take it from different cosets, you can go to a common, you can write both cosets as a disjoint union of common cosets and prove that. So, the thing is, the set of idempotents of this conjugates of EA actually forms a commutative semigroup. So, that is the first crucial observation. Oops. So, you look at the span of these idempotents and look at the idempotents in that span. So, the first thing is this actually forms a commutative semigroup. The first thing you prove is, once you prove this, you look at this set, you just create an inverse semigroup out of these unitaries and isometries, and you also put a 0. So, then you can show that this is actually a star semigroup of partial isometries. That is, every element here is a partial isometry, and moreover any product of them is again a partial isometry and again of the same form. So, this actually forms an inverse semigroup. And your Cuntz-Li algebra, that is actually you will have a representation of this inverse semigroup in the Cuntz-Li algebra. So, you can apply Paterson's machinery to construct the groupoid. So, one can apply the inverse semigroup machinery to study this thing, which is actually a quotient of this C star D. Actually, one has to apply Excel's theory of tight representations. It is, if you construct Paterson's groupoid, you won't end up getting the correct groupoid as what Cuntz-Li has done. So, you have to restrict your groupoid to, so Paterson's groupoid is made up of all characters. You have to restrict your characters to what are called tight characters or maximal characters. There is a very neat conceptual way, and this is due to Excel. So, one can apply Excel's theory of tight representations to answer this question. So, you take this inverse semigroup, you just construct the Excel's groupoid, which is similar to Paterson's groupoid, and you end up getting the same groupoid as what Cuntz and Li has done. So, So this gives a very nice, neat conceptual way of doing it. So thank you. Any questions? Sorry.
So this application of inverse semigroup to the Cuntz-Li thing is your work.
Yes, yes, yeah. Yeah, that's my word. Thank you.
Also get some new system algebra.
No, the Cuntz-Li thing is only originally for any integral domain with finite quotients, but you can also do it for semi-direct product. You can also do it for my basic motivation was to extend it for the semi-direct product Q and semi-direct product JL and Q. You let JL and Q act on Qn and do that, whether those results will extend or not, and it does extend, and you can use inverse semigroups to study them.
Only one philosophical objection. Then gamma in the JL and Q.
Yes, yes, yes.
You will look at non-separable inverse test. You said you look at N2 gamma.
Gamma in what?
You say gamma is any subgroup of JL and Q, right?
JL and Q.
JL and Q.
Yeah. Not JL and R.
Not JL and R.
That's why I looked at JL and Q. So. Yeah, the K theory computation was done by Kuntz and Li for ring C-star algebras. Using this duality theorem, you can prove it for the C-star algebra associated with any integer dilation matrix. But I am trying to understand the K theory computation for groups like JL and Q and so on. So for that, one needs sophisticated machinery like bomb cone and those kind of things, which I don't have any idea of. So.
Any other comments, questions? If not, let us thank him again and all the speakers.
Thank you.